Next up is Plan B. Plan A was to heavily restrict the first condition for a data race, concurrent execution. And we did that with JavaScript, and primarily that was eliminating parallelism, but there was also a control on how concurrency worked. Concurrency was restricted in that every task or task execution was atomic. That was Plan A. Then Plan B is going to be to eliminate the second condition for a data race, and that is having shared data. Now, I don't have any concrete example with code of eliminating shared data, but this is something that comes up and it's a potential solution to the problem. The one that we've seen that definitely works this way is doing parallelism with fork. If you have one process and you fork it, then you have two processes, and those two processes don't have shared memory. We did copy on write copying of all the mutable state, unless we explicitly requested shared memory with mmap. And since they're not going to share memory, that means they're not sharing any data. They therefore can execute concurrently or in parallel without any data races. We have this question of how do we do inter-process communication in that case. We have to solve that problem. One way to solve that problem is to add shared data back in. That gives us data races back in, but by default, when you fork on a Unix-style system, you don't get data races. The next sort of general solution is message passing. You have two or more concurrently executing processes. They don't share memory, but instead of sharing memory, they communicate by sending each other messages. One really common example that you'll hear about a lot if you listen to people talking about developing sort of web architecture is microservices, where you write one program to handle one piece of the system, you write another program to handle another piece of the system. Those two programs are executing separately, maybe in separate containers, maybe on separate servers, maybe on separate virtual machines. And they don't share any state, but they do talk to each other, or they both talk to the same database. And that is a way to try to reduce data races by eliminating shared data. Similarly, in traditional cluster computing, we're running code on multiple physical machines. Since the physical machines have separate physical memory, it doesn't really make sense to try to simulate shared memory, although some systems do that. But by default, in systems like MPI, the idea is we don't have any shared memory. Instead, we do message passing, and therefore, the way we have to deal with data races is a little bit different. There tend to be a lot of barriers in MPI-style programming, even though eliminating shared data tends to imply that we've eliminated data races. There are still other sort of parallelism problems that you have to deal with, and you frequently want to try to write code where you aren't really worried about exactly what order things happen in, so there's still a little bit of coordination that needs to happen. And then finally, we can have message passing just entirely as a pattern. For example, in the Go programming language, the way they recommend writing code that runs in parallel is to use a mechanism called channels, which is Go's mechanism for message passing, rather than having a variable that's shared between multiple. They call them Go routines. They're lightweight threads. And by avoiding having a shared variable, you can still have your memory be shared, but if it's in a variable in one Go routine initially, and then you pass that data to another Go routine where it gets put in another local variable, then that's the same sort of thing as a barrier. We know that before it's passed as a message, thread A can access, read and write that data. After it's passed as a message, thread B can read and write that data. And since no two threads ever have ownership of that data at the same time, we've avoided the data race. So that's plan B. Next up, the obvious third plan.